Students, today my topic is alcohols and phenols. So alcohols may be defined as hydroxyl derivatives of hydrocarbons, and this may be derived by replacing one or more hydrogen atoms of alkanes by the corresponding number of hydroxyl groups. In the given equation, the compound alkane, one of the hydrogen atom is replaced with a hydroxyl group, then we can obtain alcohol. Another point is, according to the nature of parent hydrocarbon, an alcohol may be aliphatic or aromatic. In the aliphatic alcohols, they have common formula CnH2n plus 2 OH or simply ROH, where R is alkyl group. Say for example, C2H5OH. Here C2H5 is the alkyl group, OH is alcoholic group. So it is said to be ethyl alcohol. Another one, aromatic alcohol, where hydroxyl group is present in the side chain. Here, best example is benzyl alcohol. It contains C6H5 CH2OH. The next one, classification of alcohols. Usually, alcohols are classified into four important classes according to the number of OH groups or hydroxyl groups present in the compounds. The first one is monohydric alcohols. These alcohols contain only one hydroxyl groups. Example, methyl alcohol. In this structure, one OH group is linked to methyl group. Another example is ethyl alcohol. So here the hydroxyl group is linked to ethyl group, that is CH3CH2. So these two compounds contain only one hydroxyl group. So they are called monohydric alcohols. The second one is dihydric alcohols. Di means two hydroxyl groups. So if the alcohol contain two hydroxyl groups on different carbon atoms, they are called dihydric alcohols. Example, ethylene glycol. In the ethylene glycol, two OH groups are present on different carbon atoms. The third one is trihydric alcohols. These alcohols contain three OH groups. See, in the given example, glycerol or propane 1,2,3 triol. Here, three OH groups are present on different carbon atoms. The last one, polyhydric alcohols. Usually, these kind of alcohols contain more than three hydroxyl groups. See, in the given example, it has more than three hydroxyl groups. The best example is mannitol. Mannitol contains polyhydric OH groups. The next one is, depending upon the number of carbon atoms, which are directly attached to the carbon atom that is bonded with the OH group, alcohols can be classified into three types. They are primary alcohols, secondary alcohols, and tertiary alcohols. In the primary alcohols, one carbon atom is directly attached to the OH group. In secondary alcohols, two carbon atoms are directly attached to the OH group. Tertiary alcohols, three carbon atoms are directly attached to the OH group. So the given example, primary, secondary and tertiary. In the primary alcohol, one of the carbon atom is directly linked to the OH group. In the secondary alcoholic, two carbon atoms are directly attached, where in tertiary alcohols, three carbon atoms are directly attached to the OH groups. Hence they are primary, secondary and tertiary alcohols. Coming to the next topic, types of monohydric alcohols. So the above primary, secondary, tertiary alcohols can be explained with the help of the following. Monohydric alcohols are divided into primary, secondary and tertiary alcohols depending upon the nature of the carbon atoms to which the functional group, that is OH, is attached. So the first one is primary alcohol. The hydroxyl group, that means OH group, is attached to the primary carbon atom. In the given examples, say for example ethanol, where hydroxyl group OH is directly attached to the primary carbon atom. In propane 1-ol also, the OH group is attached to the primary carbon atom. In third example, 2-methyl propane 1-ol, here also the OH group is directly attached to the primary carbon atom. Coming to the next alcohol, that is secondary alcohol, if the OH group is attached to a secondary carbon atom, such kind of alcohols are said to be secondary alcohols. So in the given examples, the OH groups are linked to secondary carbon atoms. The next one is tertiary alcohols. Here OH group is attached to tertiary carbon atoms. Say for example, the last one is tertiary alcohol. Remaining two alcohols, one is primary and another one is secondary. In the primary alcohol, the OH group is linked to primary carbon. In the secondary alcohol, the OH group is linked to the secondary carbon. Whereas in tertiary alcohol, the OH group is linked to tertiary carbons. Best example, tertiary butyl alcohol, where OH group is linked to the tertiary carbons. The next one is preparation methods of alcohols. We have several methods for preparing alcohols. We have the first one is from organometallics or organometallic compounds. The best example for organometallic compounds Grignard reagents. Usually Grignard reagents are alkyl magnesium halides. General formula RMgX, where R is alkyl group, Mg magnesium, X stands for halide. Grignard reagents on reaction with carbonyl compounds. Carbonyl compounds are the compounds which contain carbonyl group. Usually we have two kinds of carbonyl groups. One is aldehyde and another one is ketone. So Grignard reagents on reaction with carbonyl compounds forms alcohols. In this reaction, a suitable Grignard reagent, the formula is RMgX, is treated with aldehyde or a ketone to form an addition intermediate product. So this addition intermediate product, which is further decomposed by water, aldehyde gives secondary alcohols while ketones gives tertiary alcohols. So primary alcohols are obtained by formaldehyde. So when we use formaldehyde, we can get the product is primary alcohol. So this is the general reaction for preparation of alcohols from organometallic compounds. So the carbonyl group, when reacts with Grignard reagent, it will give addition intermediate product, then which is further decomposed by water. The carbonyl group is converted to corresponding alcohols. So this is the preparation method for alcohols from Grignard reagents or organometallic compounds. So in the above explanation, that is general reaction, here in this slide we have some examples. So in this slide, when formaldehyde or methanol on reaction with Grignard reagent, it will give an intermediate and thus decomposed with water, it will converted into primary alcohol. Whereas in case of ketone, when reacts with Grignard reagent, it will give tertiary alcohol. These are the examples for preparation of alcohols from organometallic compounds. Other than formaldehyde, remaining aldehydes, depending on upon the number of carbon atoms, we will produce secondary alcohols. That is the second reaction. The second preparation, Dept-Blanc reduction. By using Dept-Blanc reduction, we synthesize alcohols. When aldehydes, ketones, acids and derivatives, here derivatives are acid chlorides, when treated with sodium and ethyl alcohol, give the corresponding alcohols. The given examples, first one is aldehyde, that is acetaldehyde. when acetaldehyde is treated with sodium and ethyl alcohol, that will give the corresponding alcohol. So here, when acetaldehyde is when treated with sodium and ethyl alcohol, it will give ethyl alcohol. So here acetaldehyde gives ethyl alcohol. In the second example, the carbonyl compound is ketone, that means that is acetone. Again, acetone when treated with sodium and ethyl alcohol, it will give isopropyl alcohol. The third one is when acid derivative, that means acetyl chloride, when treated with ethyl alcohol and sodium, it gives ethyl alcohol. The next one is reduction of esters, preparation of alcohols from esters. Usually, primary alcohols are formed from esters by the following methods. The general reaction, the ester when treated with sodium and ethyl alcohol, it will give alcohol. For example, ethyl propionate. When ethyl propionate, when treated with sodium and ethyl alcohol, it will produce propane 1-ol and ethanol. The next one is chemical properties of alcohols. Alcohols exhibit a wide range of spontaneous chemical reactions due to the cleavage of the CO bond and OH bond. Some prominent chemical reactions of alcohols are oxidation of alcohols. Alcohols undergo oxidation in the presence of an oxidizing agent to produce aldehydes and ketones, which upon further oxidation give carboxylic acids. So in the given example, the general example, when primary alcohol undergoes oxidation in the presence of oxidizing agent, it will produce aldehyde, which upon further oxidation to give the carboxylic acid. So primary alcohol will be converted to carboxylic acid by oxidizing agent. Primary, secondary and tertiary alcohols behave differentially towards oxidizing agents. We have several types of oxidizing agents such as potassium dichromate, alkaline potassium permanganate, nitric acid. So when primary and secondary alcohols oxidized by dilute solutions of acidic potassium dichromate or acidic or alkaline potassium permanganate or dilute nitric acid. Tertiary alcohols are oxidized only by strong oxidizing agents under vigorous conditions. Say for example, when primary alcohols are oxidized first to aldehyde and then two carboxylic acids. Here, both having the same number of carbon atoms as the parent alcohol. The best example, when ethyl alcohol oxidized by dilute solutions of potassium dichromate in acidic medium, that is in sulfuric acid. In the first step, ethyl alcohol is converted to aldehyde, that is acetaldehyde. After that, then further oxidation, it will give acetic acid. Here, the carboxylic acid and aldehyde having the same number of carbon atoms as the parent alcohol, that is ethyl alcohol. The next one is when secondary alcohols are oxidized to ketones having the same number of carbon atoms as the alcohol. Ketones undergo oxidation under drastic conditions, giving a mixture of acids containing lesser number of carbon atoms. In the given example, propane 2-ol, it is secondary alcohol. This secondary alcohol oxidized to ketone, that means that is propanone, having same number of carbon atoms as the alcohol. Propanone having 3 carbon atoms, propane 2-ol, that is parent alcohol, that contains 3 carbon atoms, both compounds having the same number of carbon atoms. So after formation of ketone, further oxidation, the propanone undergoes oxidation to give mixture of acids. Mixture of acids here, acetic acid and methanoic acid. So both are having less number of carbon atoms when compared with the parent alcohol. After further oxidation, acetic acid or ethanoic acid and methanoic acid undergoes further oxidation to produce carbon dioxide and water. Whereas in case of tertiary alcohols, on oxidation under vigorous conditions, they yield ketones and then acids, both having less number of carbon atoms than the parent molecule. So when tertiary alcohol, that is 2-methyl butane 2-ol, on oxidation under vigorous conditions, they yield ketone and acids. So both these are having less number of carbon atoms than parent molecule 2-methyl butane 2-ol. The next topic, distinction between primary and secondary tertiary alcohols. We have some differentiating methods. Those are Lucas test, Victor Meyer test, and oxidation test. We have already discussed these oxidation tests. So the first one is Lucas test. The mixture of anhydrous zinc chloride and concentrated hydrochloric acid is called Lucas reagent. When tertiary alcohol reacts with the Lucas reagent, gives white color turbidity immediately, whereas the secondary alcohols, when reacts with anhydrous zinc chloride and concentrated HCl, gives white precipitate or white turbidity after few minutes. Primary alcohols does not give white turbidity with Lucas reagent. So by using Lucas reagent, we can differentiate the tertiary, secondary and primary. The next test is Victor-Meyer test. When alcohol is reacted with phosphorus and iodine to form corresponding alkyl iodide. This is the first step. These alkyl iodide react with silver nitrate to form corresponding nitroalkanes. The nitroalkanes is then reacted with nitrous acid followed by treatment with alkali, that means NaOH, gives different colors. So when primary alcohol gives red color, secondary alcohol gives blue color in the Victor-Meyer test, whereas tertiary alcohol does not give any color. So by identifying the corresponding colors, we can distinguish primary, secondary and tertiary alcohols. The third one is oxidation tests. We are already discussed in the above slide. So for better understanding purpose, how can you distinguish alcohols? So we have two types of methods. The first one is Victor-Meyer's method. The second one is Lucas test. So in Victor-Meyer test, primary alcohols gives red color, secondary alcohols gives blue color, and tertiary alcohols does not give any color. So this is Lucas test. We already discussed. So these are the reactions of primary, secondary, tertiary alcohols with Victor-Meyer reagents. So in the primary alcohol, red color, secondary alcohols gives blue color, tertiary alcohols gives no color, colorless. So this is Victor-Meyer method to distinguish alcohols. Red color primary alcohol, blue color secondary alcohol, and a tertiary alcohol, it does not give any color. So this is Lucas test. The next one is phenol-quinone rearrangement. Very important topic. The acid catalyzed rearrangement of vicinal diols. That means 1,2-diols to ketones or aldehydes with elimination of H2O or water is known as pinocol or pinocol-pinocolone rearrangement. The name was given from the classical example of the conversion of pinocol to pinocolone. Here, vicinal diols means if the compound contains two OH groups which are present on adjacent carbon atoms. Those are vicinal diols or 1,2-diols. Here the best example is pinocol, where two OH groups are present on the adjacent carbon atoms. This rearrangement is applicable to 1,2-glycol. It involves the shifting of methyl group from one of the glycol carbon atom to the other. Coming to the reaction mechanism of pinocol-pinocolone rearrangement. There are 4 mechanism steps. The first one is the base OH. The group is present on the one of the carbon atom of the 1,2-diol, which accepts a proton H plus from sulfuric acid to form protonated glycol. The protonated glycol then loses a molecule of water or H2O to form a carbonium ion. Carbonium ion means carbocation. The carbonium ion then undergoes 1,2-alkyl shift to yield more stable carbonium ion. Finally, the more stable carbonium ion loses a proton to form pinocolone. This is the mechanism of pinocol-pinocolone rearrangement. Coming to the next topic, phenols. Phenols are the chemical compounds that have a benzene ring linked to hydroxyl group. If the OH group is linked to the benzene ring, such compounds are called phenols. They are sometimes referred to as carbolic acids due to their extreme acidic character. So here the OH group is linked to benzene. It is phenol, also called benzenol. The second one is where the benzene ring is having two OH groups on first carbon and third carbon. So 3-hydroxyphenol is also called resorcinol or 1,3-benzene-diol. 1,3-benzene-diol. That means benzene ring contains two OH groups. One of the OH group is present on the first carbon and the second OH group is present on the third carbon. The second one is preparation of phenols. We have different methods of preparations of phenols. The first one is preparation of phenol from cumene. Cumin means isopropyl benzene. Isopropyl benzene is called cumin. See, cumin is a hydrocarbon is used to make phenol. In the presence of air, cumin is oxidized to cumin hydroperoxide. So which on treatment with acid forms phenol and acetone. This method also produces a significant amount of acetone as byproduct of the reaction. So in this reaction, not only synthesizing phenols, but also we can produce acetone as the byproduct. The second preparation from diazonium salts. At 273 to 278 Kelvin, an aromatic primary amine is treated with nitrous acid. It can be prepared from sodium nitrate and HCl to form diazonium salt. Diazonium salts are hydrolyzed to phenols by heating them in water or treating them with the dilute acids. So here primary amine is aniline, where aromatic ring benzene is linked to NH2 group. So amines are the general formula RNH2 or ARNH2. Here aromatic primary amine. If the NH2 group is directly linked to the aromatic compound, that is aromatic primary amine. In the first step, aniline reacts with nitrous acid. Here nitrous acid can be produced by treating NaNO2 with HCl to form diazonium salt, that is benzene diazonium chloride. These diazonium salts are hydrolyzed to phenols by heating them in water or treating them with the dilute acids. In this reaction, nitrogen and HCl are byproducts. Physical properties of phenols. Usually, pure phenols are generally colorless solids or liquids and acquires light color on exposure to air. Coming to the boiling points, phenols have high boiling points as compared to corresponding hydrocarbons. Alcohols, it is due to intermolecular hydrogen bonding. The third property is solubility. Phenols are soluble in water. It is due to strong hydrogen bonding between phenols and water molecules. The next one is very important reaction in phenols, Reimer-Tiemann reaction. When phenols react with chloroform and sodium hydroxide or potassium hydroxide solution gives hydroxyaldehydes. This reaction is known as Reimer-Tiemann reaction. For example, when phenol reacts with chloroform CHCl3 and sodium hydroxide solution at hot condition gives hydroxyaldehyde, here salicylaldehyde and 4-hydroxybenzaldehyde. Salicylaldehyde is the major product, 4-hydroxybenzaldehyde is minor product. This reaction is called Reimer-Tiemann reaction. The second one is Kolbe-Schmidt reaction. In Kolbe-Schmidt reaction, when phenol is treated with sodium hydroxide, sodium phenoxide is produced. The sodium phenoxide, when treated with carbon dioxide, followed by reaction with acid, undergoes electrophilic substitution to give orthohydroxybenzoic acid as the major product. This reaction is known as Kolbe reaction. So in the given example, phenol is treated with sodium hydroxide. Sodium phenoxide is produced in the first step. The sodium phenoxide again treated with carbon dioxide at 400 Kelvin at 4 to 7 atmospheric pressure under the pressure conditions. It will give sodium salicylate, that is orthohydroxybenzoic acid derivative, and then this reaction is called Kolbe's reaction.